So I shall just go on endlessly. When people get too restless, I'll have to stop. But anyway, what about string theory? Well, let me say something about string theory. And I'm going to start with the good things, which is what I did with quantum mechanics, I think. It really, sometime in the 1970s, it's been going on a long time, actually. It started from sort of trying to go beyond the standard rules of particle physics, which involve, usually done by things called Feynman diagrams. You have to imagine this is meant to be sort of space-time picture with time going up the picture, and these are different processes which can take place between particles. And the thing is, what you've got to do is add them all up, because these are different things that might happen. And if you remember, in quantum mechanics, if one thing might happen, or another thing might happen, or another thing might happen, you've got to consider these superpositions, complex number weighted superpositions. And that's a perfectly standard procedure which works brilliantly in particle physics, except for the fact that if you really stick to the rules, you find the answer is almost always infinity. This is a pink infinity, not a black one, which means it's not the one I've been talking about before. It's a bad answer. If you get infinity, that's nonsense. So you have to think of clever ways of getting around this infinity. And there are all sorts of extremely clever ways of doing it. And when they work, they sometimes work absolutely superbly to give brilliant answers. So there's something true in all this, even though you keep getting the answer infinity. But string theory was trying to get around this and say, well, suppose point particles aren't really points, but they're little loops of some kind of thing, not actual string, of course, just loops of some kind, described by little loops in space. And then the history of that thing would be a sort of tube like this, you see. As time progresses, that loop would describe this tube. And then these processes would be described by tubes joining and disconnecting, and so it's a brilliant idea, beautiful idea. I had no question about this. When I first saw this, I thought this was amazingly attractive, not only because of the picture being nice, but because, well, these things combine up. You see this topologically the same as that, whereas these are different, and then you start to see certain relationships which are not obvious when you see it this way. But also, these things can be treated as what are called Riemann surfaces. What's a Riemann surface? Well, it's really a vessel plane, complex numbers, bent up into a surface. And they have all sorts of extremely beautiful mathematical properties. There's no question of it. You just take your vessel plane, fold it up, glue them together, and so on, in such ways that preserve the complex number structure, and that's what these things are supposed to be. And the mathematics is extremely elegant. There's no doubt about it. So that's the good stuff. And it certainly attracted me. What started to worry me is when string theory, that's for the early days, since the early days, it evolved in certain ways, and one of the main ways that it evolved is in dimensionality. One way was that the strings didn't have to be just little loops of string. They could be higher dimensional things. In fact, they're different things. They're the p-branes. Membrane is where it comes from, and then you think of p-branes, and that's supposed to be a pun, I should tell you. And there are also things called d-branes. That's quite different, because d isn't a number. It stands for Dirichlet. Anyway, that was the funny picture I drew you earlier, you see. I was trying to represent a d-brane. Don't worry any more about it, because I'm not going to say any more about it, mainly because I never understood them. They just sit there for some reason to make your life either better or worse, depending on your point of view. But anyway, what was more uncomfortable for me is that the space-time dimension had to go up from 4, initially to 26, then it came down a bit to 10, and then it went up a little bit to 11, maybe. I'm not even quite sure, as people seem to say that the dimensionality depends on the energy, which is a rather worrying idea for various reasons. But the question is, why don't we see the extra dimensions? And the argument tends to be, well, it depends on how closely you look. If you had a hose pipe, it might look like a one-dimensional thing, just like a piece of string. But if you look at it with a magnifying glass, you see it's really got a surface, which is two-dimensional. And so the idea is that the space-time we're familiar with is a bit like this hose pipe looked at from a distance. When you get up close, you see it's got all these extra dimensions. But there is this problem of excessive functional freedom, which is not something that string theorists seem to worry too much about. Of course, you could say because of quantum mechanics it's a more complicated, subtle issue, which indeed it is, but it doesn't get around the problem. I just want to make a remark here, comparing it with what's known as Kaluza-Klein theory. This was another theory when people tended to, it was an early 20th century theory, a generalization of Einstein's general theory of relativity, which is supposed to include electromagnetism. It's a very ingenious trick. But the thing is, it's not really like string theory. People said, well, you know, these people did this a long time ago, even Einstein took to the idea quite, so why wouldn't he like this idea, and so on. But there is a big difference, and that is that in this Kaluza-Klein theory, you impose a symmetry around this hose pipe. So this is space going this way, and this is the extra dimension going around that way, and it has a certain symmetrical structure. It's really the same all the way around. And if it's the same all the way around, that means your functions don't have a dependence around this way. They only depend on these variables. They don't depend on that one. So it's not like this. In string theory, the functional freedom does include going around this way. That's part of the whole point. And so you say, well, why don't you see all this vast excess of freedom in your functions, which should be just flopping all over the place? Well, the argument is like this. They say, standard string theory argument is it would take too much energy. It's something like a Planck scale energy. Planck scale is the sort of quantum gravity level. Maybe it's a bit more than that, but anyway, that sort of scale, which is ridiculously larger energy than anything you can produce on any feasible particle accelerator. But this is really looking at the problem as a particle physics problem. And the thing is that once you've excited the mode of vibration at all, you've done it for the whole universe. So this means we should be thinking about things on the scale of the whole universe. Some kind of nonlinear instability or something like that. Why does it have to be a particle interaction? And if you think about that, then you see no reason why these shouldn't get activated. And once they do, there are classical theorems that tell you that the thing will rapidly become singular, will encounter infinite curvatures. So it's pretty bad news. That's classical, of course, and you may be saying, well, shouldn't we think properly quantum mechanically? But you can also use this argument to show that really this is something that the quantum mechanics shouldn't have kicked in yet at that level. So it seems to me a serious worry. So you might say, well, why do people not worry about these things? Well, I'm not sure I know why they don't. I've said this enough times, and I've not had really a good answer about why not to worry. But one reason they think one shouldn't rock the boat is things like this. And let me just show you this. This is one of the sorts of supports.